Yes, Doctor. Yes. Please. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, I welcome you to the 6th week of workshops under the umbrella of the VP for Research. Today is our turn at the Center for Advanced Materials to introduce three prominent speakers actually from inside and outside Qatar. You know all the challenges of the water desalination. It's a matter of life here in Qatar, since Qatar relies on desalination almost 100%, let me say like 97, 98%. So it's really an essential and vital issue that actually bombarding the life of everyone in Qatar and in the GCC region in general. By 2030, 50% of the oil production in Saudi Arabia, for example, will be consumed for water desalination only. So it's a really, important issue to target in research and also, of course, in industry, which is the reflection of the research at universities. In order to make the story short, let me introduce our first prominent speaker here, Engineer Vignesh Iyer. He's a technical manager for desalination and wastewater at Metito overseas in Qatar. He has over than 25 years of experience in water treatment, desalination, and wastewater treatment sector in design and estimation. He started his career in 1996 in India with Aquatech Industries for 2 years, and then he moved for 5 years in Ion Exchange India Limited as a pioneer water treatment, which is a pioneer water treatment company in India. He was responsible for tendering and design of water treatment projects in India, including proposals, preliminary design, and cost estimation for filtration plants, demineralization plants, and RO plants, both BWRO and seawater desalination by reverse osmosis. He joined international water and desalination company Metito overseas in UAE in 2003 for 18 years, and he was responsible for the proposal preparation, technical, and process design for strategic projects in Middle East. He joined Metito in Qatar in 2010 and responsible for design of Pearl Qatar desalination plant, which produces almost 35,000 cubic meter per day in 2010 to 2011. In the last 10 years, from 2012 onwards, he was responsible for technical interface on all desalination water and wastewater treatment projects in Qatar for power plants, refineries, oil and gas, and infrastructure projects. Engineer Vignesh, the floor is all yours. So we all, eager to listen to your talk. So please go ahead.
Thank you. Thank you, Doctor. Thank you for this introduction. It is a pleasure. On behalf of myself and my company, Metito, it is a pleasure for me to represent this August forum and discuss the desalination topic. As you rightly said, sir, desalination is a very hot topic. There are a lot of, although the industry and the technology has matured enough, however, there are lot of challenges which we all face all over the world, and specifically in GCC region, and more specifically in Qatar. So thank you once again. Let me move on to the presentation slides. I'll make it short. I will not go into the fundamentals, okay? However, I just want to share a screen on the broad technology of desalination using reverse osmosis technology. So what we have seawater coming into a feed tank from a seawater intake system. Typically, you have the process treatment, the first treatment, what we call the pre-treatment unit, which starts with a DAF, dissolved air flotation unit. We will talk about it more in details, what it does. And then the water from the DAF, it goes to a filtration process, multimedia sand filters to remove turbidity. Again, polishing filters, cartridge filters, what you see on the right side, the white color filter. And after all of this pre-treatment, which is step 1, step 2, step 3, then the water further enters into the heart of the RO technology, which is the reverse osmosis skids through a high pressure pump. So RO high pressure pump on the, what you can see on the center on the right side, followed by a 2-pass reverse osmosis skid of pass 1 and pass 2, where the bulk of the salinity of the seawater is reduced. And further, after the water comes out from the RO, we all know that we have to have a post-treatment to make the water suitable for potable purpose and drinking purpose. So what you see on the bottom left side is the final step called the post-treatment, after which the water goes to a product water tank, what you see on the bottom left. Now, having said that, we all know that there is a reject water or a wastewater which is generated from the desalination. This water is taken to a reject water tank, and then from this tank, it is further taken for sea disposal. All the reject water has to typically go back to the sea. So this is in broad what we call as a technology selection. So what is involved in this technology? So we all know the seawater is having algae, it is having oil, it is having suspended solids, total suspended solids, TSS, silt density index. This is very high in seawater. So this is what is removed in the first 3 steps in the pre-treatment. Then you have chemical dosing systems to minimize scaling on the membranes. You have to also remove chlorine, because chlorine we all know is poisonous for the membrane. So you give a dechlorination by using something called sodium bisulfide to remove chlorine, and then of course the heart of the process, as I mentioned, the reverse osmosis skid, post-treatment, and last but not the least, the pH correction, so that the water is suitable in case it is to go for drinking use. We have to correct the pH to make the water eligible for drinking. Now, having seen the treatment scheme, let me straight away jump into what are the challenges, okay? And then I will move on to how we address the challenges in Metito by using some innovative technologies. So broadly, we have the major challenges. The first and the foremost is a receding coastline. You know, we all know that there is pollution due to discharge, especially in the Gulf. The Arabian Gulf is a very narrow strip of sea, unlike the other areas in the world where you have the Indian Ocean, the Pacific Ocean, which is more open. So in the Arabian Gulf, especially when the reject water is discharged, it causes pollution. So this is the most important challenge. Due to the pollution, the coastline, you know, the clean water coastline is polluted, and it leads to the receding of the coastline. Again, not to mention the construction activities happening all around us. Especially, we all know that the Pearl Qatar, for example, is a man-made island. So it was a sea 15 years back, 20 years back, but then it was the dredging of the sea happened into turning into a community. So that is where we say receding coastline. Number 2, algal bloom. Now there is a very interesting phenomena in Middle East specifically, which is not happening throughout the year, but sometimes there is some phenomena called algal bloom or red tide. What is this? Due to the pollution, there is algae formation in the water, seawater. And this algae formation, especially in summer months, it can be very complicated. There is a red patch of water, what you can see, a red color water. So this has to be addressed. And typically the desalination plants which are there in the world do not have treatment for algal bloom, because this is a region specific problem. So we have to address algal bloom, red tide. The other challenge, especially in GCC area, is a very high salinity. Again, this is because of the Arabian Gulf, which tapers as we move on from Oman, UAE, Qatar towards Kuwait. We all know the geography. The Arabian Gulf tapers. So it is like a closed circulation. So you have high salinity due to the increase in the concentration of the water. There is a high salinity. There is no open current or circulation of water, unlike the other oceans what we have. So high salinity. Now, point number 4, boron. Now, stringent requirements for drinking water. As we know, most of the GCC countries, the desalination is done for having the water for potable use or for drinking. Now, let me talk of Qatar. The Qatar Electricity and Water Authority have implemented 5 years back a stringent regulation to follow World Health Organization standards for drinking water, one of the important parameters is boron. Now, this boron has to be specifically treated in the desalination plant to achieve the stringent levels specified by WHO. And two other challenges, high temperature, especially when we have the cooling water return line in the industrial setup like Ras Laffan, where the water is taken from the sea, passed through a cooling water circuit, but the return line, where does this go? This goes back to the sea. So there is a delta T because this is a cooling water. So the water coming back to the sea, it has a high temperature, a delta of 2 to 3 degrees compared to the seawater. This is another challenge. Wastewater recycle, we all know the concept of wastewater. All major organizations are implementing wastewater recycle due to the environment regulations specified by the Ministry of Environment. So we have to adapt the RO technology for wastewater recycle. And then one of the points is the corrosion. We are all staying besides the sea. Typically the desalination plants are within 500 meters from the sea. So we have the corrosion taking place, which reduces the equipment life of the desalination plant and increases the replacement cost. So these are the broad challenges. I will quickly move on to how all stakeholders, technology companies, Metito and other companies are addressing these challenges. We have various ways of bringing in innovation, okay? We spoke about red tide, okay? A phenomena due to the algal bloom. What we have is advanced pretreatment. So what does it mean? The conventional pretreatment, which takes place in other parts of the world, will not be sufficient. You need to add extra pretreatment steps to control this algae or to treat the high level of oil in seawater. This is done by using the DAF. If you go back to my first slide, DAF, dissolved air flotation. You give this to as an additional unit in pretreatment for taking care of algal bloom. Second is for the boron, to meet the boron, and for the high salinity in the Gulf area, you go for a 2-pass RO design. So there is one RO, the product water from this is further taken to a second RO. Typically in other projects worldwide, you will only have a single pass. But in Gulf, in Middle East area, you have to go for a 2-pass design on a specific basis to achieve the treated water quality. Now, there are special boron membranes available, which we have to use to take care of the high salinity and boron. Similarly, to address the high temperature of the cooling water return line, there are many companies, R&D companies in the world, like Mitsubishi, like Chevron, ConocoPhillips, who are now working on high temperature membranes. Means what? A membrane, special membrane which can handle high temperature seawater. So you can use it for the cooling water return line. A conventional membrane will typically handle temperature only up to 38 degrees. But sometimes you need to have a high temperature membrane. Lot of innovation and study is going on at present on this aspect. Last but not the least, the metallurgy. Because of the corrosion issue, we have to use some exotic material, super special metallurgy, like something called super duplex stainless steel. Now we all know stainless steel, we all know duplex stainless steel, but with the salinity in Gulf area, they don't work. So you have to go for something called super duplex stainless steel. In technical terms, there is something called PREN number, which has to be greater than 40 to ensure that the metallurgy is sufficient for the long life of the plant. So these are the various points I wanted to touch upon. I know we have a limitation of time. I will just end my presentation to show you some sample photographs of how a typical reverse osmosis skid in the industry looks like. So what you see here on the left side, these are the RO skids, the white pressure tubes. What you see, that is a pressure tube. Inside those white pressure tubes, we house the RO membranes. So here you see a more clear photo. This is a skid with the pressure tube, and each pressure tube typically has 7 to 8 membranes. So this is a photo of a typical desalination plant, which is a typical large desalination plant. That's all from my side. Thank you, and I'm open for any questions.
Much, Engineer Vignesh. Can we keep the questions to the end of the talks?
Sure.
Then we can just start the discussion regarding the three talks together.
This is fine.
Thank you so much. Thank you. Thank you, everyone. Now we will go to the second presentation by Professor Ali Kilij. Professor Ali Kilij is an associate professor at the Istanbul Technical University. During his MSc and PhD, he studied on engineered fabrics such as nanofibrous filters, polymer additives, electric aerosol filters, and related equipment manufacturing. He is also vice manager of TMAG Labs, which was established in 2003 at the Gumulcu campus of Istanbul Technical University. The studies are concentrated on interdisciplinary field of engineered fabrics and design and manufacture of specialty instruments for such materials. Focusing on novel fiber and nanofiber application, TMAG facilities are divided as filtration and separation, energy and composites, and biomedical labs. Center also houses state-of-the-art facilities for product development, analytical services, material testing, analysis, and evaluation. So far, Dr. Kilij, with his team, designed and manufactured novel nanofiber fiber production systems, including electro spinning, solution blowing, centrifugal spinning, electro blowing, evaporators, wet spinning, melt spinning, and melt blowing. Professor Ali Kilij is the author of more than 40 SCI index journal articles, 3 patents, and about 8 book chapters. So, Professor Kilij, I will let the floor for you. So please start your presentation. Thank you.
Thank you very much for introducing me, Professor. So I'm going to share my screen with you. So, as Professor introduced myself, I'm a professor in Istanbul Technical University and working on the novel textile materials actually. So these textiles are actually used for some technical applications. So they are called also technical textiles. Here is the outline of my presentation. Can you see my presentation? Oh, I'm sorry, it is taking 4 slides. Yeah.
Yes, we can see you.
So the thing is, today I'm going to talk about nanofibers. So these are these exhibit some specific factors, specific performance parameters. There are some novelties in the production and application of nanofibers. So today I'm going to talk about some new systems to make them more available, to scale up the systems to go for larger machines, larger productions. So here are some methods I'm going to talk today, and also there will be applications of nanofibrous membranes in water desalination. And also, since you are all working in environmental sciences, there are some also pretty important advancements in the filtration and face mask applications. I'm going to talk a little bit from them. So firstly, let me introduce you the nanofiber technology. So they are generally mentioned to be the one size, which is fiber diameter less than 1 micrometer. You can here compare with human hair. So we can reduce the fiber diameters down to 50 nanometers. Actually, here I mentioned as 0.2 micrometer, but we can reduce it to 50 nanometers. So this brings us very high surface area. This brings us very high porosity, and also this makes us the users of these kind of materials are very versatile. We can use them in various applications, from water desalination to aerosol filtration, from energy storage materials to medical applications. So here you see comparatively how they are making. So they are pretty smaller than cotton or even silk fibers. The thing is, mostly known as electro spinning, most of the laboratories over the world has electro spinning system. This easily gives us idea about the fibers, the spinability of some polymers, meaning that if we form fibers using electrospinning, it means that some polymers, this polymer can be spun into fibrous materials to be used in textile or technical textile applications. So as I said, electrospinning is quite basic, easy system. So what we are doing is we do have a syringe pump. We do have a syringe to feed. Regular medical syringes are used, and also kind of collector. It can be moving or it can be stationary. We are applying a high potential between this between the needle tip and also the collector. So under this huge electric field, it forms fibers by means of some electrostatic forces. So if we go through, we can see that there are many parameters that are affecting electrospinning actually. So due to that reason, actually, electrospinning is a kind of difficult when we go for large-scale production. The main reason actually we can mention two of them. One of them is use of very high potential. This increases some safety concerns on electrospinning. Plus it uses too high electricity. I mean, the electricity expenses is going high. And on the other side, since these electrostatic forces are kind of weak forces, the system's productivity is not so large. So after I come back to Turkey, we focused on two novel systems in this regard. So here is, as I mentioned, we are using electrostatic forces, but we said that what if we use compressed air? So using compressed air, we can form again some fibers, and compression is kind of larger forces is applied to this polymer jet. After doing some preliminary studies, we saw that we were able to increase the feed rate to very high values, which is 10 times of the electrospinning. And on the other side, since we do have higher mechanical forces, the solution concentration can be larger, And another study we focused was use of the centrifugal forces. So we do have a special type of spinneret here, and by means of centrifugal forces, we are forcing polymer jet to form some fibers. This is again, these two systems are again mechanical, fully mechanical systems. Even for centrifugal spinning system, we were able to increase the productivity of the system up to 30 milliliters per hour. This is just per nozzle, per one nozzle. I mean, the comparison is done for only one nozzle. Again, due to use of mechanical forces, we can increase the solution concentration to 15%. This is quite important because this increases the, again, productivity of the system. I'm going to show you some videos so you can understand it better, I believe, using this cartoon. I hope it is going to work. You can reach also from YouTube. So you can easily see how the fibers are formed from this video. By the way, Areka is our spin-off company that we produce those of the, I'm sorry, videos are generally problematic when it comes to, yeah. Yeah, I'm going to show solution blowing right now. So here, as you see, we do have a collector. This is the lab scale system. We do have pilot scale systems as well. So we do have this specially designed nozzles for that purpose. You probably see the fibers just coming. You know, it is quite highly productive compared to electrospinning. By means of compressed air, we are forming the fibers, as you see. So the nanocentrino is our centrifuge spinning systems. As you see here, we are feeding the polymer from here, and by means of centrifugal forces, I don't know if you can see the fibers here. So they are very distributed. This is generally called as the cotton candy mechanism also. This is basically used for the cotton candy production, but for production of membranes or filter products, we have to have a homogeneous uniform surface. And what we did is, lastly, we combined both systems, electrostatics and compressed air, in our latest product. So we combining these two forces, we try to enhance the productivity plus maybe reducing the fiber diameter further below 50 nanometers. So as you see here, we are utilizing from both compressed air and charging of the system. So these both are working in the system. So these systems are pretty facile and versatile to produce nanofibers and to make them useful for the membrane products that we are using, membrane cartridges used in desalination. Another system is actually the world is looking for some systems which are recyclable. So for that reason, rather than using solutions here, we are using kind of thermoplastic polymers to produce nanofibers, non-woven structures. Here, as you see, the system, it is quite versatile. It can go up to 150 centimeter width, and you can produce again nano macrofibrous membranes using the same system. So this is melt blowing system. This is the fourth system I was able to explain to yourselves. There are some other systems also. Some of them are quite difficult to produce. Some of them are, the materials dependent. For instance, these are self-assembly, island phase separation, and template synthesis. They do have some advantages and disadvantages. So I'm not going to mention for them, but I can answer your questions over the systems as well. So what can we do with nanofibers actually? We are working with Dr. Javaid also on this thing. Nanofibers actually, if we check for the conventional nonwovens, these are the substrates used in membranes. We are able to reduce the pore sizes down to 10 micrometer pore size. So it means they are not so good for membrane applications. If you go nanofibers, even going down to 50 nanometers, since they do have fibrous structures, it is quite difficult to reduce the porosity actually lower than 1 micrometer. So please keep this in your mind. Due to that reason, we are making some modifications on these nanofibers. So these are like, if we press on them and if we make them more like a membrane structure, porous membrane structure, hot pressing is one method. We can use some cross-linking techniques. And also at the end of the day, what we can do actually, the best performance we were able to obtain is, we are using the nanofiber layers as the mid layers. So they are fibrous mid layers. They do have high tortuosity. So due to that reason, use of nanofibers, especially when we go for these our membranes, use of nanofibers gives us opportunity to go for high water permeability. So for that reason, generally interfacial polymerization is utilized. And you can design your materials down to reverse osmosis, nanofiltration, and ultrafiltration membranes. Here, there are some examples from different applications. For instance, graphene oxide is also used to set their morphology. You can make some changes on your nanofibers here, whatever the nanofiber, you can make some chemical modifications. You can go for the CVD applications. So those of the systems are very possible. So imagine that if you do not use nanofibrous mid layers, you are going to use for instance, phase inverted membranes here as the mid layer. But these nanofibrous layers do have high porosity, meaning that water can penetrate easily through this mid layer. So otherwise, if you do not use nanofibers, you are going to use kind of maybe microfiltration membrane under this interfacially polymerized layer. So this is causing a lot of pressure for the water to permeate. So nanofibers, as I said, basically for desalination purposes, we have to concentrate on these mid layers, and if we put something over them, we can enhance the performance quite larger degrees. There are some novel applications other than reverse osmosis membranes. So nanofibers are also doing good in this regard. They are used in some FO membranes, and for instance, in some studies, they were able to increase the water permeability up to 300% increases can be mentioned. So here you see actually the main mechanism. We are firstly producing the nanofibers over our substrates, and after that we are making this interfacial polymerization to go for reverse osmosis, nanofiltration, and microfiltration membranes. If we can manage some changes in the structure, we can also make changes. We can also reach such membrane performance. For instance, when we use PVA is a very environmentally friendly material. When you go for instance, UV curing over these nanofibrous layers, this also forms kind of membrane structure, and this is also can be used for nanofiltration, ultrafiltration applications. Nanofibers gives us opportunity to follow the requirements of the water filtration. For some specific applications like membrane distillation, we may need for super hydrophobicity or hydrophobic surfaces. This is also possible with nanofibers since it mostly depends on the chemistry of the selected polymer. But we can easily arrange the hydrophilicity, the chemical resistance. For instance, even for PVA, which is water soluble, if you go for some cross-linking, even the PVA nanofibers, it stands the required chemical resistance. And other parameters, as I said, porosity, this is basically where nanofibers are doing best for the membrane production. So we do have high porosity compared to other membranes. So this porosity allows the permeation of water, which you can see here actually. This is from a resource also. As you see here, for regular membranes, flux is quite low here. And if we go for nanofibrous structures, even very similar rejection rates, you can increase the flux up to 50%. This is quite good number, I believe. This is quite nice improvement to produce the membranes. I believe compared to traditional systems, this is going to work in the coming years. I strongly believe that. As I said, there are some also these other applications of membranes. Membrane distillation is one of them. Here we do have, for instance, we can also arrange the surface properties. We can change the tortuosity that water penetrates actually. So this kind of tortuosity is very much can be arranged if you go for nanofiber production systems. There are also, these are for, and here the membrane processes I already explained. There are also some novel applications that are really doing good. Nowadays, people are arranging a lot, even in industry, not only academia. For instance, one basic idea to go for is one successful applications of nanofibers and these fibrous structures for water reclamation is use of water harvesting. This is like fogging things. So nature gives us very nice ideas in this regard. For instance, this is taken from a kind of specific spider. If we use that, we can easily harvest the water from the fog. And even this animal, this was created in such a nice, surface chemistry, let me say. So due to this surface chemistry, this animal never ever drinks water. So utilizing from the humidity changes during the nighttime and daytime, these animal, due to this surface, this super hydrophobic and super hydrophilic surface ductors, we can easily capture the water as droplets, and these droplets just go through its mouth, and it is just obtaining the water from this mechanism. So these are some systems, for instance, mimicking the structure of these insects. So if you go for the spider silks, they are just changing the structures accordingly using the nanofibers, and water harvesting was also possible from this way. Another idea that is quite interesting, and also right now it really got quite long, we can utilize from photocathetic oxidation. So this is used in both in water and air filtration studies. So general titanium dioxide or zinc oxide are the basic materials. These are used for photovoltaic applications as well. So since they are producing some oxidants in the structures, we can somehow obtain clean water using these systems also. And as you see here, for some dyes, especially or creosol and methylene blue, it is quite possible to form such pools, and using the nanofibers again. Here, nanofibers are used as the carrier for these photocatalyst materials. You probably know this titanium dioxide and zinc oxide, these kind of photocatalyst powders are in powder form. They are in powder form. So we cannot put them into the pool directly because otherwise it is going to cause particulate contamination. So due to that reason, we can store them over these nanofibrous surfaces and they are going to act again. As you know, due to this pandemic, we do have quite important things ongoing with the air filtration. Air filtration became very critical all over the world. So there are some numbers I'm not going to mention, but especially these pandemic conditions and this indoor air pollution is quite problematic. And they are also used in hospitals and many plants. So for that purpose, also nanofibers find applications. This is kind of different compared to membrane separation techniques. Air filtration is not like this similar separation technique. So for the air filtration, we can capture particles from different distances, and there are some mechanical filtration and electrostatic filtration mechanisms. So we follow these mechanisms. If we reduce the porosity of the samples, again, we are able to enhance the filtration performance. Another important gain when we use nanofibers is the flow again. If I sum up, the nanofibers are basically increasing the flux or flow rate, even for air or water. If we reduce the nanofiber diameter below 100 nanometers, the air, when it hits it, it is making a motion which is called slip flow, meaning that the velocity of air does not drop to zero when we use for microfibers. So when we use nanofibers, the air just slips over the nanofibers, and due to that reason, we are going to be in lower pressure. So lower pressure drop is again arranged by the nanofibers, and this is a graph for penetration and clogging. This is for air filtration. And again, the similar structure might be used. Photocatalyst, I already mentioned this mechanism. This is also used to remove any kind of odors, any kind of VOCs in the air. So the same is used for, we are using again nanofibers for these structures. For gas filtration, this titanium dioxide coated nanofibers are quite useful materials. And regularly we are using activated carbon, as in the case of water filtration things. But if we go for titanium dioxide, we can easily reach better VOC removal rates. So here there are some current internal collaborations that we are holding, and we are very lucky that, alhamdulillah, we are collaborating with Dr. Javait in this case. We already signed a memorandum of understanding with Qatar University. We are very happy to do that. And with all our facilities to produce these nanofibers to make their tests, we are ready for future collaborations. So I thank you very much for giving me the opportunity to make this presentation. This is all from my side.
Muslim University in India, and his master's degree from Chemical Engineering Department in King Fahd University of Petroleum and Minerals, and his PhD from the Chemical Engineering Department at Laval University, Canada. He has more than 25 years of teaching and research experience in the area of clean water and clean energy. He has worked in King Fahd University of Petroleum and Minerals, Saudi Arabia, the University of Queensland, Australia, Laval University, Canada, and has been visiting scholar at the Massachusetts Institute of Technology, USA. He has extensive experience in the desalination research and have supervised many graduate students in clean water and clean energy disciplines. He has published more than 300 papers in international journals, book chapters, conference proceedings, and has 14 US patents and patent applications. He has conducted joint projects in reverse osmosis desalination in collaboration with the Massachusetts Institute of Technology, USA, for the development of nanostructural membranes for reverse osmosis water desalination. He also has collaborated with industry and provided technical support into industry in water technology and clean energy projects. He was the founding member of the Center of Research Excellence in Renewable Energy, a national research center in Saudi Arabia, and board of director members. He was the member of Research Advisory Board of KFUBM, headed by His Excellency, the Rector of the KFUBM University. And he was the coordinator of desalination research in KFUBM, member of National Unifying Efforts in Desalination in KSA, Saudi Arabia. And also he presently honorary member of Advisory Council of Arab Water Desalination. He is the recipient of many national and international awards, including KFUBM Excellence in Research Award, Patent Award, Al-Mari Prize for Research Innovation and Lifetime Achievement Award by the Venus International Foundation. Professor Zaidi, the floor is all yours. We are eager to listen to your presentation. Thank you.
Yeah, thank you, Dr. Abubakar, for your nice introduction. So, after the two speakers who has given a background about the RO technology, I will give you a brief background about the desalination activities in Qatar and how the trend shifting from thermal desalination into reverse osmosis desalination. And this is just a quick fact that the water scarcity, as we know, is the defining feature of the 21st century, and by 2025, 2/3 of the world population will suffer water shortages, and compared to today, by 2050, 5 times you will have land under drought. So by 2050, 1 in 5 developing countries will face water shortages. So we have total currently around 15,900 desalination plants in the world, with a total capacity of around 96 million cubic meter per day. And the fact is that most of them are located in this region where we are in the Middle East. That more than 50% capacity is in the Middle East. So there are these two desalination technologies. We have thermal-based desalination and the membrane-based. And in the beginning, most of the desalination plants were based on thermal technology, which is multi-stage flash and multi-effect desalination. And in the Middle East, they were based on that one. But worldwide, the trend is that more than 60% of the plants are based on RO desalination because of the energy efficiency and environmental effects. As you can see here, this RO desalination, this is the specific energy consumption and carbon footprint. You see here with different technology, RO has the lowest carbon footprint and has lowest energy consumption. So that's why people are moving from thermal to RO, which is more environmental friendly and more less energy consumption. Now coming to the Qatar. Now Qatar, as you know, is surrounded by the water from all the sides, 3 sides, and we have no fresh access to fresh water. So it is very strategically important to the state of Qatar, and water is one of the grand challenges of our National Vision 2030. So they have been good working for the innovative technology development to minimize the cost of water and reduce the environmental effects. So as you see here, the Qatar, we have absence of natural resources, minimal rainfall, high evaporation rate, and due to urbanization, we have, as you see, the massive infrastructure development in Qatar. The industrial water growth has increasing as well as the domestic water. But at the same time, there were challenges because Qatari water, as mentioned by previous speaker from Metito, that the water in Qatar is very complex. It has high salinity, high TBS, algal blooms. We have high temperatures, high wind, turbidity, just facing more pressure on the your pre-treatment technologies. So this is about the total desalination capacity. As we see here, the more than 60% desalination capacity, 65% is in MENA region. Okay? And most of it, and worldwide, you see here that the trend for the technology is on RO. But in the Middle East, we had in the beginning, all our plants were based on thermal desalination. The reason was low energy cost because it is abundantly oil and cheap available, and at the same time, no co-power generation. They were producing power, so they were having mega plant. Now that the shift is changing from thermal to RO. As you see here, this is the Arabian Peninsula. You see here high desalination concentration of desalination plants. You can see in the region. In this one, oh, sorry, this one. So in the beginning, you see here the RO, the share of RO was only 6%. It was 6%. As I told you, because of the low energy cost, they were based on thermal desalination. Now the trend is changing. You can see here, the RO has grown from 2012 until 2021. You can see here, the share of RO has increased from 12% to 24%, or more than around 175% increase, whereas the trend for other thermal is stable. So because, as I told you, because of less energy consumption, they are modular in nature. You can have big systems, you have a small system, whatever is based on the requirement, and they use membrane and a small footprint. There's very low emission of CO2, and they are environment friendly. Coming to the Qatar, as I told you, 75% of the technology was based on MSF, and RO share was only 1% before 2010. Now, after 2010, the new plants were built in Qatar on the mega scale by the government of Qatar, QEWC, Qatar Electricity and Water Company. Now the share of water of RO technology has increased around 40%. And we have last year, in 2018 or 2019, we have there's commissioning and installation of one of the largest desalination plants in Al Hul, which is the largest in the whole Middle East for RO desalination. This I'm talking, giving statistics about the Qatar QEWC plant. In addition, we have so many plants built by Metallurgy company installed in different locations. So you can see here there is a jump, shift, exponential shift of technology from thermal to RO in Qatar, which is exponential increasing. That is, more and more plants are coming again. So giving this few facts, now this is a schematic of a typical RO process. It has two sections. We have pre-treatment, we have the membrane section, and we have post-treatment. As has been explained by Mr. Varghese, we're giving some detail, but pre-treatment is very important because in order to protect the downstream membrane for RO. So here there have been a lot of innovation, as we mentioned there. Here they are using dissolved air flotation, which has not been used in other parts of the world because the complexity of water is not as complex in other parts than here. So they have been using ultrafiltration also, like in some plants in Saudi Arabia, in Dubai and other places. So now the heart of the process is RO, because RO membranes approximately contribute around 30% of the cost of the total desalination plant. So and the RO membranes, there have been a lot of development, but in order to increase efficiency and cost, a lot of innovation are taking place in this one. So we also have been working for the development of the membrane, next generation membrane we call TFC, or advanced thin film composite membrane. So there are two types of membrane which have been used in RO. One are based on cellulose acetate, we call CA, because they are such, and the other one, a later generation called polyamide thin film composite membrane. And they are, because the CA are susceptible to biological attack and limited to chemical stability and low pressure, so later this led to the development of the TFC thin film composite membrane. And the polyamide TFC membranes, they are the standard of industry now, and they have been widely used, but still there are some issues. So this is how the structure of a membrane look like, and consists of three different layers. One is the top layer, where which is the main separating layer, and it is very thin. This is less than 1 micron. This is about less than half of a micron. We can say 1/10 of a micron. Then you have middle layer, which is made of polysulfone, and that provides pathways for water. And we have the polyester layer, which provide the mechanical strength. This is how the structure of a thin film composite look like. So the benefit of TFC that you can independently control, that each layer can be controlled independently. You have desired permeability and selectivity can be achieved. It has good compression strength as well as excellent mechanical strength, but in spite of that, there are some limitations and drawbacks. For example, they are not resistant to chlorine. So there is separate treatment for dechlorination has to be done before the water goes to the RO process. So they are sensitive to fouling, especially the biofouling, because even though RO technology is very mature, well developed, but still biofouling and organic fouling still remains an issue. And inadequate boron rejection efficiency. So we have development cellulose acetate membrane, we have TFC polyamide membrane. Now people are a lot of working for next generation of membrane for the development of fouling resistant, chlorine resistant RO membrane, the better flux. So at Qatar University, we have been also working for the development of the RO membrane, and we use two different approaches. We have used also nanomaterial. As you know, nanotechnology is playing a big role in each field of the life in our research, in our scientific community. So we have a lot of nanomaterials have been used and proposed. So here we have used two different kind of nanoculars, which are very abundantly used material, naturally occurring and cheap material. And also we have used a different manufacturing or fabrication technique. The currently used TFC membrane, they are made by interfacial polymerization. There is some complex manufacturing process. So we try to make a simpler process. So these are two studies we undertake. We have used two nanomaterial, one called montmorillonite and the other one is colloidite. And they are incorporated in the thin layer of the top layer of the polyamide in very low percentage, less than 1%, 0.2, 0.5%. And this we have first time we have validated the effectiveness of these nanoculars. So these are some of the performance results you can see here. This is on the left side average water flux, right side is the salt rejection. So as we increase concentration from 0.1% to 0.5%, even very small incorporation composition, they have shown very promising results with two different nanoclays. So at the same time, they have shown very high hydrophilicity, which is indicated by the contact angle. So they have very high contact angle, both of that kind of the membrane. The another one is study, which is based on a technique called layer by layer deposition, or spin assisted layer by layer assembly, where we have used two different electrolyte, two pairs of electrolyte, which are a combination of two strong electrolyte and weak electrolyte, PTAX, PVS, PH, and PS on the polysulfone support. So here idea is we did not use completely interfacial polymerization to completely eliminate the PL layer and use simply a combination of different electrolyte, different layers of strong electrolyte, the positive charge and negative charge layers deposited one after the other. So these are the result of AFM microscope showing the surface roughness. You see here, the first one is the bare polysulfone substrate. There's no polyamide, and we deposited 60 layer, 100 layer, 150 layer. But you can see here the surface roughness has decreased. They become more smoother because the more the rougher the membrane, they are more susceptible to biological effects, biofouling and bacteria form. So these results are very good. We have applied patent for this one. These are the results for the filtration performance. So we have the water flux on the left side. On the right side, we have salt rejection. You can see here the membrane showing a promising performance, high water flux as well as high rejection. So these two layers, two different combinations. So our study demonstrated that these TFC membranes are promising, and these novel fabrication techniques are great tool to manufacture our membrane. And we are still optimizing and studying further to optimize technology. And the important thing is the key drivers for commercialization of this technology need to be identified in order to expedite the industry adaptation in the near future. And we have industry partner over here, so I'm mentioning And also, I would like to mention we have been partnering with Matito on our different projects and CRP and other projects. And at the same time, I would like to mention here, we also have established a water technology unit in Qatar University under the umbrella of Center for Advanced Material, under the leadership of Dr. Nasir Al-Naimi, who is our director, and we are collaborating with industry, and we are open for industrial collaboration as well as for academic collaboration overseas, and we are trying to establish as a whole center. Thank you very much for your listening.
Thank you so much, Professor Zaidi. I will just invite Engineer Vignesh and Dr. Zaidi for the panel discussion. We don't have much time left anyway, but just I will take quick questions from the attendees first. If anyone has a question, or if we get question from our listeners over the internet, I cannot see them here. So any questions for the speakers? Okay, if there's no question from here, I just have a few questions for the speakers. Engineer Vignesh, you mentioned that the super duplex stainless steel is one of the solutions to overcome the corrosion problems in the desalination plants. What about the cost, and are there any other choices other than duplex stainless steel? My point is, when the deposition happens, the local chemistry under the deposition is completely different from what's surrounding. So even if you have super duplex stainless steel, it will not, survive the high acidity and high chloride concentration ions under the deposit. So if we have another option, because the super duplex stainless steel, the cost is very high. So if we have like titanium, for example, what do you think about these choices? Thank you.
As high as 20,000 milligram per liter. So yes, to answer your question specifically, there are different types of exotic materials available. Like other than super duplex stainless steel, we also have something called CD4 MCU. We have titanium. But then when we compare the cost, typically we have done that exercise in Matito on the large scale projects. All of them are in the same league of the high exotic cost, So what happens is we need to also look at the commercial availability of these materials. So what happens is when we talk of the high pressure pump, so it's not only a theoretical selection, but we also have to look at that whether the pump manufacturers in the world, what is commercially viable for them, what is the range of the pump selection. Similarly, for the piping, we have to strike a balance between super duplex stainless steel availability, because there are a lot of challenges, especially in terms of production of very specific metallurgy of pipes in the desalination industry. Yes, so there are a couple of factors, but yes, we do look at different materials before taking a final call on what is to be selected.
Thank you. My question is to Dr. Ali, Professor Ali Kilij from Istanbul University. So regarding the scale-up of the nanofiber production, this is number one. And number two is, the production of nanofibers have some challenges, for example, the stability of the morphology, effect of humidity, and so on. So how can you target such challenges, and what do you say about the scale up of the nanofibers? It's easy process, or it also has some challenges? Professor Ali, can you hear us? Professor Ali? Professor Kilij, can you hear us? I think we lost him. So I will go. Next question, Professor Zaidi. Is it possible, this is a question from Dr. Mariam Al-Ajji, is it possible to tackle the issue of boron in pre-treatment stage before going to, before going to the DAF process? Can we just take another pre-treatment step to remove the boron?
Yes, sir. Thank you. This is the question is regarding a boron removal, right? Yeah, actually they do in the pre-treatment stage, but at the same time there have been some work going on to develop the boron-resistant membrane in the same RO membrane. So, like you can have in the PA layer deposition of some of the nanomaterials, so that it can effectively remove boron. But again, it depends on the seawater quality. Like some of the issues in some part of the world, they do not have boron issues. Some part of the world, they have this boron concentration which is above the limit. So this, if the concentration is high, they put a separate a pre-treatment step in combination with those steps. And at the same time, they can be combined with the current membrane, the work going on, to modify those membrane, PA membrane, the TFC membrane, which take care of boron removal.
Just one last question here from Arnold Jansson. He's asking about the RO membrane flux. How can we improve the RO membrane flux through innovation, and as long as the ultimate cost of production, the pumping energy would still remain the same because of the it is osmotic pressure driven. So he's asking how can we improve this, without on the expense of the energy consumption. So this is therefore Engineer Vignesh. So if you can.
Yeah. So when we talk of the RO flux, typically what happens is that this is directly related to the capacity of the membrane to handle the per cubic meter of water. Okay, so the membrane meter cube versus the area of the membrane available for the volume of the water to be treated. So the lot of research and innovations are going on in terms of developing the more fine porous membranes, advanced type of structure of the membranes to optimize this flux. Because especially I still remember 15, 20 years back, when we were designing the desalination plants, we were very conservative on the flux rate. But then due to the technological advances, we have now come up with more relaxed flux rates. At the same time, not compromising on the overall performance of the water quality. So this is the balance what we try to strike in terms of selecting the RO flux.
Yeah, Dr. Zaidi.
Yes. To continue this, there is a possibility, because now especially there are new materials which is very promising with the advent of nanotechnology. Some nanomaterials like graphene oxide and CNT, they have shown a promise that the water flux has been shown very improved tremendously. And there is a material they developed, they call Profene, which is based on graphene oxide, and one company in the US, they are developing these membranes. So of course, these nanomaterials are helping to improve, to increase the water flux as well as the efficiency of the membrane. So yes, this is possible going on.
So just one last question and we will conclude. How do you compare the future of the RO compared to the other new technologies like capacitive deionization or solar concentrators and so on? So how do you see the future of the RO compared to the other new technologies?
Yes, as Professor Zaidi has also shown in his slides, the increasing trend of the desalination market, in which the thermal desalination has gradually shifted to the reverse osmosis plants. We would only see a further increase in this direction, because what is happening is, especially not only in terms of energy of the electricity consumption, but also in terms of the cost of the membrane. Now, what we see here is the trend is due to the more variety of selection of the membranes and advancement. Practically, the membrane cost has reduced by 40% what it was 10, 15 years back, you know. Of course, then you have other factors like competition, because membrane is a very niche product and there are very few membrane manufacturers all over the world, you know. It's not like equipment like a pump or a filter where you have many manufacturers. So we have like maximum 3, 4, you can just count if you talk of reputed membrane manufacturers. So we would see that the RO technology is very matured and is going to eventually replace in the long run in terms of the overall life cycle cost. If you compare, yes, and we have seen that in Middle East in the last 15, 20 years. So we see this phenomena only increasing, and eventually we will have most of the desalination plants by RO rather than by other process like thermal or MED.
Thank you. Dr. Zaidi, you like to comment?
Yeah, I would like to comment, yes, when you're talking capacity of deionization, first of all, this is still in the development stage. There is no proven the data, and even that there is no demo plant. So if you compare with DI, then we can have forward osmosis as well. Okay, so RO is very mature technology, which and continuous development has been taking place, and capacity DI technology still it is in the I see the lab scale. So we cannot commit at present because again it also depend on you also use the membranes, cations and exchange anion exchange membranes on those one also. So and also the issue of the again the scaling up at the larger scale. And lastly, I would like to comment just on the since we have coronavirus issues. So I just would like to comment one thing. I have a slide, but I could not show that RO membranes are very safe to corona. The coronavirus size is about 100 nanometer, where the size of the pore size of the RO membranes is less than 1 nanometer. So they cannot pass through the RO membrane. It is very safe to drink water which is treated by RO. So there is no issue of that because sometimes there were concern we have been reading in the news not now a few months back about what issues it's just safe to drink. So it's very safe to drink water from RO. Even Corolla because of the virus size is much bigger than the pore size. The membrane of the RO completely removes. Okay.
Thank you. Thank you so much, Professor Zaidi. Thank you so much, Engineer Vignesh.
Thank you.
And thank you, Professor Ali from Istanbul Technical University. Thank you so much for all our attendees and all our listeners over the internet. Thank you so much, and see you in the next round. Thank you so much. Take care.
Thank you.